the master in the electrical engineering in the CINVESTAV in Mexico also, and her PhD on the automatic control computer vision and robotics from the Polytechnic of Catalonia here in Spain. She also did postdoctoral in France, and now he's working on Australia in Sydney. Main research interest is robotic perception, multisensory data, self-localization, mapping, etc. So thank you for coming, and you're ready to go.
Yeah, thanks, Paulo, for the introduction. Yeah, so today I'm going to talk about on our work on continuous models for sensor integration, localization, mapping, and planning. But yeah, first I'm going to introduce a little bit our research center and a little bit of myself. Well, already Pablo mentioned it. So now I did my PhD in Barcelona in the Institute de Robótica and Informática Industrial, postdoc in LAAS, and another postdoc in ACFR in Sydney Uni, and moved to ETHZ, where I'm now associate professor. So this is the outline of my talk. I'm gonna first give a brief introduction of the ETHZ Robotics Institute, and then I'll continue with the topic of today. It's split in two parts, one about the implicit surfaces and the other one about inertial integration. Okay, so the Robotics Institute is in Sydney, Australia. So we have the famous Opera House and the Sydney Harbour Bridge. And beautiful beaches. So if you, it's a great place to visit, but also to work. The Robotics Institute recently has been converted from the ETHZ Center for Autonomous Systems to the ETHZ Robotics Institute. I mean, that only gives us a bit, it's just a change of name, but that gives us a little bit more of autonomy. And yeah, becomes a bit bigger because it includes everybody from the university working in robotics. So today we are around 70 people, like including PhD, 10 academics, like around 10 postdocs and 50 PhD students. Well, PhD and master students, but mostly PhD students. We do research in sensing, perception, estimation, human-robot interaction, planning, and robotic systems. And we have a teaching component where we teach around, there is a Mechatronics program around more than 500 students, and we also have a master's in robotics. One of some of the highlight projects, and don't worry, I'm not gonna go through, these are all lengthy videos, but I just kind of want to highlight the type of projects that we do, the applied projects that we do at the Robotics Institute. Are, for instance, in the infrastructure maintenance, some of the projects, and the reason the Institute has a very good name in Australia and overseas is because of the projects on infrastructure maintenance, where we have deployed robots in, for instance, the Sydney Harbour Bridge. So there is this biologically inspired climbing robot that is currently doing inspection of the structure of the Sydney Harbour Bridge, which in some cases hasn't been inspected in, I don't know, over 50 years, because people are not allowed to go inside the structure of the bridge. And you can see here an example of the structure that the robot aims to inspect. So it builds a map and it plans its path through the bridge. And it's currently, this version is currently deployed in the Sydney Harbour Bridge. And yeah, there are another iterations. So other projects that we have a large program with the water utilities in Australia, where we have been working with them to develop technology, sensing and robotic technology that could go and inspect water pipes and sewers. So currently we have a couple of robots deployed in sewers in Sydney, and and we have a robot that every time a pipe breaks, it goes and quickly inspect the condition of this of the pipes. So another, nothing to do with infrastructure maintenance, but more on the side of train management or train station management, where we have a project with we put 3D cameras to monitor the passenger numbers and behavior in train stations. And we have a system deployed in a couple of train stations in Sydney and Brisbane. And some other work that we have on human robotic collaboration, especially for manufacturing or hazardous tasks, where we have physical interaction of human operating robot manipulators for tasks like grid blasting, which requires a lot of strength to kind of clean surfaces. We have these projects to combine the human ability to move and the strength of the manipulators to do the task. So these are roughly kind of a high-level topic projects that we have in the center. Now, some of my projects are on the my current projects are on the advanced manufacturing side. We have a lot. I'm working currently in a project about cobots in advanced manufacturing, looking at different aspects of how can we make robots, how can we improve the manufacturing industry using robots intelligent robots that could collaborate with people. Another of my projects is related to livestock and carcasses, where we use 3D sensing to understand the current condition and predict yield in all these systems. I have another project. These are more fundamental research projects where we look at unconventional sensing for robotic perception, and some of the sensors are magnetic, like microphone arrays or event-based cameras, and some few other projects that related. We have a collaboration with DLR on the perception for planetary-like environments, and I'm working also with some prosthesis glasses for blind people to be able to allow them navigate in unknown environments. So these are some of our robots. We have, from custom made to commercial robots, so a wide range of robots around the center. So we have to play with many of these, which is a lot of fun. Okay, so let's start the topic. So I'm gonna start with the continuous models for, in this case, doing implicit surface mapping, but it's I'm going to talk about this representation that allows us to do more than that. Not it's a so what I'm presenting today, it's well, the whole topic of today is about continuous models, right? For either mapping, planning, localization, sensor integration. So you will see a general trend in my talk. And I'm going to start with this Log-GPIS, which is a recent work that we published last year in RAL about a continuous representation, continuous and probabilistic Euclidean continuous and probabilistic representation for mapping Euclidean distance field and at the same time recovering an implicit surface that we could use for mapping and planning. So you could see here in this image, we have a robot moving in an unknown environment, and it's planning its path based on the Euclidean distance field, which is recovering, and at the same time, it's able to get the surface of what we call the zero crossing of this field to recover the obstacles. So how do we do this? All right, so in this case, I'm gonna give, there is a little bit of a disclosure here. I'm gonna, in the next few slides, I'm gonna have some equations. I must say a lot of equations. So bear with me, I'll try to explain most of them. But I think, I mean, it's important to go through the equations to be able to explain what we are doing in this case. And I'm going to start, this is just the standard definition of what an Euclidean distance function is, right? So we have, imagine we have the Euclidean space, and we want to find the distance from any point of the space to the surface, right? So if we can do that, we have the whole Euclidean distance field of this space. And this is just the equation that tells you. So the minimum the minimum distance is from any point to the surface is the one that we want to find through this field. And this, so the nice thing of this Euclidean distance field, this Euclidean distance function, can be captured by what it's called the Inertial equation. So imagine you have this scenario where you have a boundary, the delta S, that dilates along the normal of this delta S, which is the surface, with a unit speed, right? Like, so it's moving outside or inside, but the direction of the normal. So then the arrival time of this, the arrival time is exactly the distance. So this is described by the Inertial equation, which is called, and it's described by the gradient of the distance equals to 1, and with some boundary conditions. So the aim of the estimation of the full Euclidean distance field is to estimate this distance given some sparse measurements. Imagine from any sensor that can produce some point cloud, right? It could be a LiDAR, it could be a 3D camera. And therefore, at the same time, given these measurements, you can recover the surface. So, well, we focus that we can use this. The Inertial equation describes this whole field, and if we solve this equation, we can find the distance from every point on the space to the surface. The only problem is this Inertial equation is very hard to solve, and it's it's nonlinear. So most of the tools available to do more analytical treatments are not, we cannot use them. And most of the methods that are used, to solve this problem are numerically. Numerical methods which require discrete and combinatorial methods. Most of them, a lot of these methods have been developed from the computer graphics community for many, many years. But just, well, I wouldn't say too recently, in 2012, Crane and company publish a paper where they use an approximation that allows to solve this, to formulate the Kernel equation in a simpler way, meaning in a linear way. And that's what we're going to exploit. So Baradans use this screen Poisson equation through formulating the idea of this recovering the field of inside a manifold by something that is called the heat kernel. So, and it's called the heat kernel because imagine you have it looks like this, right? Imagine you have a needle and then you punch in the size, and how you can see how the heat propagates through a manifold or through a surface, right? And this can be described by this equation. Okay, but there is a relationship between this heat kernel and the distance, and it's very simply given by this equation, right? Like by the logarithmic, roughly the logarithmic transformation of these heat kernels is roughly the distance when the time tends to 0. So then, as an approximation, you can get that the distance is equal to the logarithmic of the kernel. And this is great because it allows us to get a form, or what we call a regularized form of this Kernel equation that we said it was nonlinear and hard to solve, to a linear relationship with the distance that it's easier to solve. Okay, so this is Baradan's result, Crane's result, and it's this is the heat kernel, or this formulation is widely used in computer graphics. All right, but this, as I said, this is formulated only in the manifold, meaning only in the surface that we want to reconstruct. But in the case of a robot navigating in the 3D space, or in the Euclidean space, we want to go beyond that, and we want not only doing it, not only consider the distance between the point inside a manifold, but the point in the 3D space, or 2D space, depending on what we are mapping. So we can, through some mathematical derivation, we can actually do that by using the complement of the boundary. But by doing this, we can use the same concept, but by doing this, we lose the sign, and you'll see why this is important, or how does the sign relate to what you probably are more familiar with, which is implicit surface. So if you are familiar with the concept of the term TSDF, or the truncated sign distance function, well, it relates very closely to what I'm talking about today. So this is called, an implicit surface can be defined by the points inside the surface and the points outside the surface. And the surface is if you can kind of classify the points, points in the, let's think about on a 2D space or a 3D space, points outside the surface are positive, or points inside the surface are negative. You can see that the zero crossing will define our surface. And that's a way to implicitly define a surface. And that's commonly used in robotics and as well in computer graphics. But more recently, or not that recently, but Gaussian process, and I don't know if you guys are familiar with, I'm not actually gonna go into any Gaussian process definition, but Gaussian process is a, let's call it a nonlinear regression approach, right? That allows us to do, for instance, fit nonlinear functions by using kernel methods. Or you can see it as well as the generalization of a function, sorry, of a probability distribution but for functions, right? So it's a multivariate Gaussian function distribution. So there, people in the past have used Gaussian processes to model implicit surfaces, and that's why it's called Gaussian process implicit surface. So this method, I mean, Williams and Fitzgibbon were the first to publish something around, but from there it has been taken on, because it's a very nice way to model this implicit surface in a probabilistic and continuous manner. But the way they do it is simply they define as a Gaussian process the distance function, and you could also avoid, so in the typical methods of mapping implicit surface, imagine you have a laser scanner looking at the surface. So you know you have a ray that hits the surface, and when it hits the surface, well, you know it is there. But you have also information along the ray, so you can tell in all this ray you have points that are outside the surface along this ray. So that's the information that we use to recover the implicit surface. But also with Gaussian process, there is a way that you don't need to define these extra points along the ray to be able to define the implicit surface. You can also define the normal through the of the surface by simply taking a differentiation of your function that is defining your implicit surface. And that's what it's, so you can have implicit surfaces and normals through this method. And yeah, and that's what we use. So, okay, so Log-GPIS, and that's our method. So this is a well-known thing. And now I'm gonna talk about what we propose. So the Log-GPIS, it's a model. We don't want to model the distance itself. We want to model the heat kernel as a Gaussian process. So then, using all the theory that I presented before, we can approximate the distance through the logarithmic of that Gaussian process. So then we have the Log-GPIS, which is how our method is called. And this is a very interesting thing, because in other literature, we've actually found that the heat kernel or the screen-Poisson equation can be satisfied using this kernel method with a type of kernel that belongs to the Mater family, which is called the Whittle kernel. And this Whittle kernel exactly satisfies the heat kernel, meaning we can solve for the heat kernel, apply the logarithmic, and we get a very good approximation of the distance. The beauty of Gaussian process is that it's a generative function, so it can generate points even where we don't have data. So that's why I call it continuous modeling, right? All right, so the only problem with the Whittle kernel is that it's not differentiable. So we cannot get normals by the kernel, by using this kernel. And that's not great, because that getting the normals for free in the Gaussian process implicit function framework it's great, and it's very useful for other things, not only for mapping, but also for planning. So we decided to use an approximation of the Whittle kernel, which is the standard Mater 3. And we evaluated how much, how close we can get to the full Whittle kernel using Mater 3. And it seems that it's reasonably good. I mean, we have a bigger error, but it's an error we could live with, as long as the lambda, as long as one of the parameters of the kernel fulfills certain constraints. All right, so I'm stopping math here, and it's just gonna show more results, which is more fun than looking at the equations. So so in our approach, imagine we receive a point cloud and 6 dot posts that can come from any localization or odometry algorithm. We feed it into our Log-GPIS framework, and we could generate a mesh, which is for visualization or mapping, and also the gradient, the Euclidean distance field of any point of the environment to the surface, which can be used for planning. So here is an example of how this is the true SDF. This is an example of how the TSDF look like, which is the truncated sign distance function that you might be familiar with, because, I don't know, Kinect Fusion and uses this representation, or many other frameworks use the TSDF representation. So you can see the Euclidean distance field, it's not really captured nicely. A simple GPIS is not great at capturing the distance far away from the surface. So once the points that we want to query are far from our data, our approximation goes to 0, because if you are using a zero mean Gaussian process, that's what it tends to do. However, if you just apply our trick, literally applying a log to the standard GPIS, you get the real, well, you get a much better approximation of the Euclidean distance field. All right, so how do we use it? So we use it for, yeah, like mapping. And so our paper was, the integral was mainly for mapping, given localization, but we are currently extending this. So you can see here, this is a simulated environment in Gazebo, where we have a bunch of bricks, and we can get a very good approximation of the distance field. We compare this to Voxlogs, which actually is one of the papers that the first papers that point out that Euclidean distance field is the thing that we need to map. We need to use for mapping, so we can do planning in a better space. So they actually propose a method to convert from TSDF to ESDF. But yeah, so their method is simply numerical, and it's not, they cannot generate they cannot generate, or they cannot run inference outside the points of observed by the sensor. Yeah, so that's why it looks in this shape and not recovering the full continuous field. And you can see there our error is in the distance, it's much lower than than, for instance, box vlogs or a standard GPIS. And this framework, despite uses a Gaussian process, is very it can be done incrementally and online. Okay, so as I said, as I mentioned, we are currently extending our framework to recover odometry as well, and with a planning framework. But that's just stay tuned. I mean, that will come soon. And we can see we have the cow and lady data set being mapped and recovering the full distance field for the 3D. We can also use it. This is with 3D cameras. We can also apply it with LiDAR data, as in the case of the Intel dataset. Okay, so I'm gonna change topics here. So if you want to ask some questions now, but you can also ask them at the end. But now I'm kind of moving from implicit surfaces to continuous pre-integration. So up to you if you want to ask some questions now, or we'll wait till the end of the talk. All right, so let's continue, and
better at the end of the talk.
Yep, that's great. All right, so now I'm changing a little bit. This is kind of the second part where I'm going to talk about our recent method on continuous pre-integration, and later how we use it into frameworks for localization and mapping. So first, a little bit of motivation of why we want, so how inertial systems work. So for instance, visual inertial have been used for a long time already. And it's you can see that in this, I'm trying to represent how the sensor data arrives. So here we'll have IMU readings at a certain rate, which is way faster than the frames that we use for vision, for visual processing, right? So, and we can also have LiDAR inertial sensors, where the problem is slightly different, because now we have 3D LiDAR points that come at we have many points that come at a very high frame rate, even higher than the IMU readings. But also we have the LiDAR scans put into single frames that come in a similar frame rate as will the image or the keyframes that we will have in a visual inertial system. So what's the problem with inertial systems are that we have asynchronous measurement. We have also a multi-sensor time shift and external calibration that we will have to estimate. But yeah, like it also, you require more dynamic motions that otherwise you will do with normal sensors, because you require to estimate biases of the inertial system. So it's kind of one sensor wants to be static and the other sensor wants motion to help their estimation of their parameter. And then you have this kind of battle between sensors of what they need to produce better data for your estimation algorithms. So in tech, and again, a little bit of I'm gonna again present some equations here, and bear with me, you don't have to fully understand all the equations, but that helps me to tell you the story of this work. All right, so we have normal dynamic systems where we have, you can express the dynamics in terms of the rotation, the rotation change rate, the velocities, and the position, right? And we have our system, let's say it has an acceleration and an angular velocity. The IMU will be measuring the proper acceleration and the angular velocity. And it will require the fact it will require to we will require to integrate these measurements to be able to have some understanding of the positions and velocities and angular and rotations, right? So bear with me, but this is just the system, how you can express it in terms of the measurements of the IMU. Oops, sorry. And you can see there is a rotation that depends on the initial orientation of the system. Okay. So a few years ago, there was the work from Lupton and Zuccaria that they come up with a very neat idea of how to decouple the initial orientation from the IMU measurements. And that's very good because that means you don't have to reintegrate if your initial conditions change. Yeah, the only thing you need to integrate is your current measurements, and that's it. And that was great and widely celebrated, and most of Inertial aided systems are using the concept of preintegration. Later, a few years later, Foster and company, they extended the work from Lupton and Zuccaria just to capture the on-manifold representation. Yeah, so the equations I presented here, they come from the Foster's paper, where they use the manifold representation. Anyway, independent of that, we have this, as I mentioned, this preintegration where we decouple the initial orientation from the measurements of the IMU, and then we can kind of use these sort of pseudo measurements, which are pre-integrated measurements that we call, and then we call it delta R, delta B, delta P. All right. So some of our work, and we started working with this pre-integration a few years back. We need, for inertial aided integration, it's important to have a continuous representation of these pre-integrated measurements or the IMU measurements in general. The reason why you want this continuous representation of these measurements is because then you can query these measurements at any time where you get information from the other sensors, right? Like the LiDAR, you could get an IMU measurement at the time of a LiDAR point or at the time of a keyframe in Vision. So we started thinking, okay, so can we fit a Gaussian process into these pre-integrated measurements? And that's what we did in a very old work, which I didn't even put here, where we just fit Gaussian processes to these measurements, and then we integrated numerically. But then we realized the Gaussian processes are a much powerful tool where we could actually analytically integrate our signals through the integration of the kernel. It's the same concept that we exploit to get normals in the case of the Gaussian process implicit surface. So this analytic integration, it can give you for free, for instance, if you have velocities, you can for free integrate to have positions. In the rotation case, it's a slightly different case, but that's what I'm going to explain now. Right, so for rotations, you cannot just simply integrate it and get, for angular velocities, you cannot simply integrate it and get rotation. That's a bit more complicated. But let's look at the case of the velocities and positions. So, okay, so this is our framework. We have 3D gyroscope, then we do some optimizations to get orientations. Then we have the 3D accelerometer measurements. Then we project these measurements through the orientation that we get. And then we can get velocities and positions. But this is done analytically integrated. Okay, so what it means analytical integration in the Gaussian process framework. I'll show you here with a kind of a visual example. So this is imagine you have, this is your signal, or this is your function, and you want to integrate this function. Well, we normally use either the rectangle rule or the trapezoidal rule, but this is done numerically, right? And you get a signal that it's integrated roughly like this, right? And this is the red line. You have some error, and depends obviously on your parameters or whatever. But it's not analytical, right? It's numerical and produces error. Okay, so with a Gaussian process, you can fit your function, standard Gaussian process regression. Yeah, you fit a nonlinear function, and through the integration of your kernel, you can recover the integral version of that, the integrated version of that function. And it's as simple as that. So this is done, I mean, this is very nicely explained in the work of Sarka. It's called Linear Operators and Stochastic Partial Differential Equations for Gaussian Processes, where he explains this. This is not a matrix multiplication. This is an operator applied to a function. And in this case, it's an operator applied to our kernel. So if we have a kernel that can analytically be integrated, for instance, the square exponential kernel can be analytically, it could be differentiate or integrate and differentiate infinite times. It's a very smooth kernel. So if we have this type of kernel, we can apply the analytical integration, and from velocity, we can get positions. So yeah, so we thought, oh, this is great. Why don't we do it to the orientations? Well, we can't. The orientation is a more complicated problem. You can integrate it for if you have angular velocities only in one axis, but we normally have 3-axis angular velocities, and with the biases, and it becomes it cannot be simply integrated to get orientations. So what we come up with in a paper that was presented in RSS last year was to do an optimization-based integration over SO3. And essentially, what we do is we learn so usually with Gaussian process, you have this, what we call the training data, right? So it's the data from your sensors and your kernel. That's what you define. And that's exactly how we get our velocities and positions from the accelerations from the IMU, right? So we have the accelerations of the IMU, we define a kernel, we integrate it, and then we get velocities and position. In the case of rotations, because we cannot do that directly, we try to learn the inducing points, or the inducing values, that's how we call it, that allows us to produce from angular velocities rotations, the rotations defined by the rotation vector, which is defined as the logarithmic of the rotation, and it's skew symmetric. All right, so the main constraint here is that we rely on the fact that this equation is right, which is the rotation on SO3. And this is a definition, well-known definition of the rotation on SO3. And this is the key thing that we optimize. So we our residual is essentially the derivative of our rotation vector times the right-hand Jacobian minus the angular velocities from the gyroscope. And then, well, we have a normalization function to prevent the thing to constrain the system. Anyway, that learned through these inducing values. So with that, we got rotations integrated from angular velocities, and then velocities integrated from accelerations, and positions integrated from the velocity. And we show that it's way more accurate than the standard preintegration method and two other preintegration methods, for instance, numerical integration methods using Gaussian processes. Of course, it's more time consuming, but we can show we can do it in small windows. In fact, you always do integration in small time windows, which allows you to run online systems. So how do we, and I'm aware about the time, but I want to show you how do we use these Gaussian process preintegration pre-integrated measurements in systems, in actual LiDAR inertial integration. So one of our systems is called IntoLAMA, which is the Inertial LiDAR Localization, Auto-Calibration, and Mapping Framework. Short, IntoLAMA. So the initial version of IntoLAMA didn't use the current UGPMs with the analytical integration. It used the continuous concept, so it uses Gaussian processes, but numerically integrated. But then we have upgraded this work to work with the new UGPMs. Okay, so what's the main problem with LiDAR inertial systems is that especially when so LiDARs are LiDAR scanners, the old style, not the solid state LiDARs. Has a rotating mechanism, meaning you don't have like a global shutter sensor. It's more like a rolling shutter sensor. So if you're moving fast, it's very likely that your scene is gonna be distorted if you consider only the time at of the first point where the scan started. Okay, so oops, sorry, I don't want to show this. I'm just gonna stop it. So the classic approach is, okay, you consider scans at certain height, certain frequency, and then assume that the scan was done at constant velocity. But that breaks completely when you are moving fast, right? Or when changing acceleration. So you get very distorted point clouds in some cases. So what we do in IntoLAMA is we consider a higher frame rate. So each point, we consider a sensor where each point has a timestamp. So we consider each point independently. And then we put it together in a scan, but through the use of this UGPM, we constrain the positions so we can undistort the point cloud. And then we recompute these features to do after we do some steps on the optimization. We formulate this as a factor graph. So we do full batch of line optimization. So if you are familiar with the factor graph formulation, which is the maximum likelihood estimation or a maximum a posteriori estimation, depending if we have prior or not, we integrate tightly the LiDAR and the inertial system. And we have, in the state, we have pose, velocities, IMU, and the extrinsic calibration and time shift. So essentially, yeah, we have this super high frame rate sensor. And then, so now the red is the LiDAR and the blue is the, well, the blue is the scan at the time that it starts, but we consider every point independent. And then we have also IMU factors. And then we can also, do bias and time shifts. All right, so this is roughly the framework, the overview of the framework, where we have the LiDAR points, where we create frames, but we use the points independently. We use the UGPMs to compute the undistorted cloud, then do the feature extraction and data association, and then we do factor graph optimization. And at the same time, we use the IMU factors to feed the optimization as well. I mean, this is a little bit of, again, this is just a graphical representation on the factor graph, where we have the LiDAR factors, IMU factors, and the the time shift and biases. Well, I'm just going to skip this. So we have a front end that uses planar and edge features. So if you're familiar with LOM, which is LiDAR odometry and mapping, that was one of the first frameworks that did this LiDAR mapping in real time. They use similar features to what we use, but our features try to capture a slightly much better the plane features. As I said, we do use the concept of frames, but we don't restrict our frames to be 360. In fact, we use larger frames because we can, right? Like you can group your points in, if you consider every point independently, you can group them in groups that are bigger than 360. And that we do back and forth association. So it becomes more constrained. So something like this. All right, so the results from Into Llama, we get we compare our results with LOM, which is not that fair because our Into Llama, sorry, this is the Into Llama I'm talking about, the auto calibration and mapping. Before we had a paper for what it's called Into Llama. It was without the auto calibration and actually didn't have the IMU factors. And adding that bit improves a lot the mapping. Okay, so we compare it with LOM, but it's not that fair because LOM runs real time. Our approach is batch and it's offline. It takes, I don't know, depending on the site, it could take up to an hour. But yeah, we can indoor environments, outdoor environments. It's not. This is the Koblenz-Landau campus dataset. Okay, so we cannot use all the standard datasets for this with this framework because we require timestamp per point of the LiDAR, and not all drivers have it. In fact, the standard ROS driver for the Velodyne or for the Auster LiDAR not only give timestamp per frame, despite the sensor can give you this information, but you just kind of have to expose it in the driver. So we had to use we can only evaluate in datasets that have drivers with timestamp, and this was one of them. All right, so yeah, last thing I'm gonna talk, and this will be very quickly, so you guys can, and we can stop. But I guess we started a little bit late, so I have a few more minutes. Is that okay, Pablo?
Yeah, sure. No problem.
No, I mean, I'm happy to stop here, but it's just, this is just a very quick to show that we can use a similar approach with event-based cameras.
Okay.
So, but up to you. I can stop here.
No, go.
Alright, so we have a framework called IDLE, which it's to work with event-based cameras. And if you're familiar with this type of camera, it doesn't give you a frame as such. It just gives you an event, still in XY coordinates in a frame. So it still uses a CCD, but it doesn't produce an image. It just asynchronous events from the scene, and usually the scene. So it's just sorry, that these asynchronous events are triggered from a change of pixel intensity. This happens usually when there is some motion in the scene, either from the scene, either from the camera. And the type of if you put it into an image, it looks like an edge detector kind of thing. It gives you XY coordinates in the image. It also gives you a time stamp. And you can also get polarity out of these images. The pros of these cameras are their very high temporal resolution, very high dynamic range. We have very low bandwidth, and it's a edge detector by itself. Main problem are this very asynchronous, well, it's an asynchronous data stream, and it's very little image information because it's not, unless you put it into an image, there is no image. So how do we use? We have a similar formulation as into Llama, where we do a factor graph formulation with tight inertial and events integration. You can see that the events could be like the LiDAR point, right? Like it's just points where we can associate an IMU reading to it. And then we estimate pose, velocities, IMU, and 3D lines. So in this case, we kind of encompass the whole thing, the mapping part, the mapping representation into 3D lines. So the GPMs allows us to accommodate for the asynchronous information. And as I said, we integrated in a similar way that we did for the into Llama. So I'm just gonna skip this. In this case, we have some other factors that allows us to deal with the kind of associating this the endpoints of a line, because we are mapping with lines in this case. So you can see this is how the events in a data set like in a data set like this look like in the time in the space-time domain. So what we do is we have this space-time representation. We segmented planes, and these planes are the ones that we use. So, well, like to produce lines. Yeah, so we get these patches, and then we get a line clustering, and we do some processing to get lines from this. All right, so yep, so essentially we do this optimization and we get, I'm just gonna skip these results, but just to show we can do localization or odometry, inertial odometry integration with events cameras, and we compare them with Robio, which is visual based. So not too fair, but at least to show that we could get results like in a kind of a similar accuracy than the visual-based sense. All right, so just a few acknowledgements. The GPIS work is done by my PhD student Langwu, and all the continuous preintegration is by Cedric, including into Llama and IDLE, which with collaborators from UTS and ETH Zurich. So as a conclusion, I presented two main frameworks, one for representation that is suitable for surface reconstruction and navigation and allows us to compute the continuous Euclidean distance field, and a continuous IMU preintegration approach, which allows us to do aid inertial systems, and we show it with a LiDAR and event camera system. And that's it. So on the shameless post, I'm looking for PhDs for 2 of my projects. So if you are interested, just contact me. Thank you.
Thank you very much, Teresa. So, I know any questions? Okay, Juan Raúl, go ahead.
Hi, thanks for the talk. It was quite interesting. A lot of the questions, it's true.
Yeah, sorry.
No. I think it was great because I think something that it was key was the integration, right? Most of the talk. And I was curious that you mentioned, okay, so we have this integration. I mean, usually you solve this numerically, but we have this method that using Gaussian process, you can solve the equation analytically, so there is not numerical error. But I was curious, like, what are the limitations of this? Because it's an analytical solution, but is the analytical solution describing the real world, or is some sort of like a?
So it's an analytical solution given the data that you have, right? So if you have very sparse data that doesn't represent nicely the function, for instance, yeah, so you will have some the error will come for the fact that you don't have enough data to capture the function itself. But if you have sufficient data, so the analytical integration is done based on the data that you have over whatever the Gaussian process fit, it integrates analytically that fitted function. So the beauty is you could tell how certain you are because you're using Gaussian process. You could also get a measurement of the variance, so you could tell how uncertain you are in the estimation of your function, given the amount of data that you get. Yeah.
Okay, thank you.
Thanks.
David.
Yeah, hi. So I would like to ask about the implicit map representation. So first, I guess that, of course, you can build it incrementally. Is it right?
Yep.
So
That's
then,
correct.
yeah. So could you comment a bit about the time performance, for example, in relation to box blocks, because that's probably the one that we all know.
Yeah. Yeah, correct. So
and also,
I can answer that.
Yeah, just one thing, and also the limitation in size of maps.
Yeah. Okay. So the implementation that we use for the Gaussian process implicit surface, it's not. Let me see if I have the time. Yeah, the computation. Oh no, this is UGP. I'm sorry. Let me just see if I can. Probably I didn't put it. Oh no. All right. Well, compared to box blocks, it's slower, probably by half. So I can tell you for this map specifically, for this, it's a very small. This is just I don't know, like around 30 frames or something like that, we can do the, okay, no, I actually have the stats. So for box blocks, do TSDF plus ESDF plus meshing in 1.5 seconds. We can do it like, we do it like way slower, but kind of 3 times slower, but it's computing the ESDF, the full ESDF, and running marching cubes to recover the surface. So and an argument is, so that we computed in 4.2 seconds. All right, so our argument is that for visualization purpose, you run marching cubes, but you don't need that real, like online. Online for planning, you need the ESDF, and potentially you don't need it. I mean, if you're in a drone, you probably want the big SDF, the full ESDF, at least in a certain area. But for instance, for mobile robots, you will want the ESDF only in one plane. So that, or in certain areas. So that could be computed much more efficiently. So we have to run matching cubes to recover from an implicit surface to get the full surface, and that takes some time. But we are like 3 times slower than box blocks.
Yeah,
And the limit of the map.
Oh yeah, see, yes, please.
Sorry. The limit of the map, actually, given the odometry, like which is what we do in the RAL paper, it's not, it kind of shouldn't slow down the whole thing, because it's done in clusters. So the Gaussian process, we don't feed a Gaussian process implicit search for the whole map. It's done like, imagine, in submaps kind of thing. So in that sense, it's not a problem. It becomes a problem when we run the odometry, which is an extension that hasn't been published yet, because then we have to we have a limit on the map that we can allocate. But given the position, it's not a limit.
Okay, thank you very much. Of course, I'm not too worried about the time performance. It was just a curiosity, because honestly, I don't think that BoxBlocks is right now like really scalable to super real time performance and so on. So I think that it's just a matter of the concept that it was super interesting. So thank you for your talk.
Thanks, David. Thanks, David. I think I mean, the BoxBlocks kind of run. It's not real time like frame rate, right? But it does run pretty decent at a pretty decent online time, so you can plan with it. And that's what we argue, that we could, with our approach, we could also plan with it if we do it intelligently. But obviously, Gaussian processes have always been the problem has been always been the computational complexity associated with them. But I think there are many strategies that we could try to that we could use to overcome some of these issues.
Okay, any other questions? Maybe if not, we can finish, so it doesn't, I don't know if there is class now, so maybe.
Maybe I don't let them go to class.
Yeah. So if there's no
thank
question,
you for staying.
Thank you for the talk. It was very interesting, and hope to see you in Zaragoza sometime.
Yeah. We'll discuss it with Javi. Yes.
Hopefully
Okay.
in June. Yeah.
Hopefully in June for Alejandro's defense.
Yeah.
Thank you.
Yeah. Thanks, guys. Thanks for inviting me. It was great to